Okay, so today we'll be talking about something which literally changed the entire game in AI, which is called the attention mechanism. And I'm not exaggerating when I say this, but this is probably one of the most important ideas in modern AI. So this concept is the reason we have many tools right now like ChatGPT, Gemini, GPT-4, or every other cool language model you've ever heard about. So hey everyone, welcome back to my channel. If you're new here, we'll break down complex AI concepts in very simplest way as possible. We have no fancy jargon, just you, me, and a whiteboard. So if that sounds good to you, you can go hit that subscribe button right now so that you don't miss any future videos. Seriously, we're going to cover everything from basic ML to generative AI, and trust me, you will want to stick around for this journey. So let me ask you this. When you're reading a book, let's say you have a book which you want to read. It's a very cool book which you have, and you really want to read this book. Now, do you give attention to every single word in that book? No, right? Some words matter more than the others, depending on what you're trying to understand. And your brain will naturally focus whatever is useful for you from this book rather than focusing on every single thing. So, that is basically what attention will do for neural networks. It will teach them to focus. So, let's just jump right in. Now, before attention came along, we had these things called the RNNs, which are called recurrent neural networks. Now, this is how they used to look like, which I'm showing you on the screen right now. And these were the go-to models for anything involving any sequences. It might be text translation, or it might be text generation, it might be speech recognition, anything. So the way they worked was pretty straightforward. They would read the input one piece at a time, like reading a sentence one by word. So let's say you're trying to translate this sentence which was given to you. The cat on the mat was very hungry. If you're trying to translate this sentence into, let's say, French, okay, so the RNN would process it in such a way that it would take the value first, which you can think the value the is here. It will try to update its hidden state. This hidden state, it will try passing it on to the next value along with the next word. So we have cat. You'll take the input cat, and then you'll make some changes in your hidden state. You'll keep moving the next way. Next on, you'll take it, you'll update your hidden state, and you'll keep moving. So on till the end. Whenever you reach hungry, the output, whatever you get, the output value of a vector, whatever you get, that it's trying to remember everything what the RNN has seen so far. So here's the problem. So by the time the RNN will get to this hungry, it's already forgotten the details about the cat in the beginning of the sentence. Now, the RNN will try and compress everything it has seen into this single fixed vector. So think about that for a second. Let's say you have Harry Potter books. Okay, if you're trying to compress all of the Harry Potter books into a single tweet, you'll definitely lose some information, right? And this will get exponentially worse when we're trying to do it with longer and longer and longer sentences. So imagine like you're translating a whole paragraph or like a whole document. By the end, the RNN will have almost no memory. Whenever you reach the end or the last word, it will almost have no memory of the beginning word. So this problem is called as a vanishing gradient problem and the long range dependency problem. And it has plagued these models for many years. Researchers did try like LSTMs and GRUs to help remember the model better. So LSTMs and GRUs were used later on to try and make sure that this approach was slightly better, but they did still have this fundamental bottleneck. You're still shoving all that information of the whole sentence into like a narrow tube like a vector. Now, back in 2014, there was a paper which had this brilliant idea of instead of forcing the model to remember everything in one compressed vector, what if we let it look back at all the previous words whenever it has to? Let's take an example. The cat ran away from the dog as soon as it saw it. Or let's say the cat ran away as soon as it saw the dog. This would be a better sentence. So let's say this is the sentence you have. Now, when you train a casual RNN on this, you'll first feed the RNN the word the, and then you'll feed the word cat. You'll feed the RNN the word ran, and then away. So on, you'll keep going until you reach the last word dog. Now, instead of that, whenever let's say you reach the word it, what if the model has a better way of understanding that the it here means that it is talking about the cat, right? That would be very interesting to do, right? Now, this is called attention. Now, when the model is trying to figure out what word to generate next or what to do next, it can pay attention to all the words it has been given before, and it can decide which ones are relevant to this. So, in this case, whenever we are talking about it here, that means we are trying to talk about the cat. Now, I'll give you a solid example to make this concept crystal clear. So, let's say we are translating the sentence, the black cat, to French. Okay, so that would be this in French. I'll try not to pronounce this so that I don't butcher any French. But when we're trying to do this, the French for the word cat is chat. Okay. So the attention mechanism lets the model look back at the entire English sentence and then assign important scores. So the cat, in this case, will get 80% of the attention, and the black value gets 15% of the attention. Let's say I'm just giving an example, and D gets 5% of the attention. Why am I giving this score? Because in this case, the cat word is more important. Why? Because it is the subject of the whole sentence. This is the most important word in this. And the second most important is, let's say, black. Why is it black? Because it's relevant, because it describes the cat. It is something which will describe the cat. And the last, which is the most irrelevant word, is the word the. Now, this barely matters for the specific word. So, can you see what's going on here? The model is like creating a custom representation based on what it needs right now. So, when it moves to generating the word noir, which means black, the attention weights will shift. Now, black might get 75% of attention, and cat might get 20% of attention when it is trying to generate the word noir in this case. So it is dynamically creating context specific representations instead of using one fixed representation for everything. Now, this is a big genius idea which they've come up with. Now, I'll show you the actual mechanism between this magic. So there's three concepts here. They are query, key, and value. Now, these three terms sound very weird and complex, but trust me, you will understand them very quickly. So let's see what these mean. Okay, think of it like you're searching on YouTube. Okay, you have a YouTube video which you want to see. You have the title, you have the metadata, whatever you have, description, the number of views, and everything. You have a search bar on YouTube as well, right? So you can think of the query as something which you would type in the search bar. Okay, something which you would type here so that it will represent what you're currently looking for. Let's say you type how to cook pasta, or how do we do attention mechanism, any video which you want to search. That is your query. Okay, so it's pretty self-explanatory what query means. Now, what is the key? Now, key is like the video title, the tags, and the metadata. It is what each video will offer so that you can find that video. You can actually find that video using the title of the video, or using the name of the channel, or using tags of that video. You'll be able to find that video. Now, that is what key means. And in value is the actual video content itself. So what you get back when you, click on the video, when you play the video, whatever content you get, that would be the value. So when you search, the YouTube video will match your query. The YouTube video will match your query against all the keys, and it will rank them by relevance, and it will return the most relevant ones. Okay, and then the value of that most relevant ones is the one which you care about. This is basically what attention does. Okay, so in attention mechanism, whatever input you have given, the first step is your input will be converted into three vectors. What is it? The query vector, the key vector, and a value vector. How do we convert this into query, key, and value vectors? It is pretty simple. All you need to do is multiply them by something called as weight matrices. Now, for query vector, the weight matrix will be denoted by WQ. The key vector, the weight matrix will be denoted by WK. The value vector, the weight matrix will be denoted by WV. Now, let's say you're trying to generate the word chat from our English sentence. So what happens is the decoder's current state will become the query. That means it will represent what information we are looking for. Okay. So each word in the English, the, black, cat, will have the value will have a key and a value vector. Black value will have a key and a value vector. Cat value will have a key and a value vector. Okay, and this vector, whatever we are trying to represent, the chat value will have a query vector. Okay, so we'll compare this query through all the key vectors which we have in our sentence. All the key values which we have in our sentence. Now, what is the best way in which we can do? We can do this by using dot product. just do find the dot product of query and key, and you'll easily be able to find the similarity score between them. So if the query is looking for the information, if the query is looking for the information about the word cat, then that means key to the word cat will get the high, will, when we multiply this query with the word key to the cat, then it will give us the highest similarity score out of all of them. And if it is compared to if it is compared to, let us say, the key value for then we'll get the lowest similarity score. So I'll just tell you with some, let's assume some fake numbers. Let's say we multiplied the query with the key value of cat, and we got something like 8.2 as the answer. For the black key value, we might get something like 3.1 or something. Or for the key value, we might get something as 0.7 or something. Now this you can see, for if you want to generate the word chat, the query value, when it is multiplied with all the key values of the other words in the sentence, you might see that, hey, the word cat is something which is more relevant to my word, which is more relevant to the word chat. So I'll try to have more context about the word cat than anything else. Now the word the is something which is not particularly needed. So you won't be considering this word much. Now, all you need to do is, you can see that the values in here are ranging from something like very big 8.2 to something very small 0.7. Now, there is one thing in machine learning or deep learning which is called as a back propagation. Now, during back propagation, what happens is, when you try to do back propagation on a simple neural network, then you'll try to upgrade the weights of each value. Okay. And when you're trying to upgrade the weights of each value, if the value of one weight is very big than the other, this value, as you keep going back the layers, will keep on increasing, increasing, increasing. And when you get to the final layer in the beginning, the value will explode and you will change the gradient by something very big. Or it is very bad if you do it in the smaller cases as well. If you take very small values, then as you keep propagating backward, these values keep diminishing small. These values keep getting smaller and smaller. And as you get to the initial value, this will shrink to almost zero. The value will almost shrink to zero, and you won't be able to update weights. Now, the extreme high case is called as exploding gradient, and the extreme low case is called as vanishing gradient. So these both are problematic. Now, how do we deal with them in this case? In this case, what we can do is, we can divide them with some scaling factor. Now, what researchers there found out was, if you divide this by the square root of dk, which is the dimension of the key vector, then that means you will be easily able to scale these values to something which is proper. So that this will help us during the training, and it will help us make sure that there is stability during the training. Now, the next step which we'll try to do is, we'll try to apply softmax. We'll try to apply softmax to this probabilities. So to this, so that we can turn this into probabilities that will turn into one. So whenever we'll take the same example for the word chat, whenever you're trying to get the values 8.2, 3.1, and 0.7, if you apply softmax, we might get something like, for cat it will be 0.72, for black it will be 0.25, and for it will be something like 0.03, let's say. So now you can see you've converted this into probabilities, and the sum of these values is equals to 1. Now you'll easily be able to see how different values will relate to the word chat in this case, right? Now there is one more gimmick. When you're trying to do softmax, the main reason we'll try to divide this by square root of dk and try to scale it is because softmax is very vulnerable to extremely large values. So if you have values like, let's say, 200 and 10 in this case, softmax will try to assign this very huge probability, something like 0.99, and it will try to assign this something very small like 0.01. Now we don't want this to happen, so that is one more reason we'll try to scale these values. Now finally, our word chat will have a context such that, hey, I can use 72% of the word cat, I can use 25% of the context of the word black, and 0.3% of the context of the word the. So in this case, what it can do is, it can go to the value vectors of these words, and then make sure that it can adjust its context in this way. So in this case, our final output would be 72% of the cat value plus 25% of the black value plus 3% of the value. Now, the beautiful thing about this is that the weight matrices that create this Q, K, and V, the weight matrices which we are multiplying here, the weight matrices are completely learnable. Okay, so the model itself will figure out how you can ask good questions, how to represent each word, how to represent each key, and how to represent each information all throughout itself by just learning. You don't have to do any engineering part to make this query key and values. You just have to initialize them with random values, and then you will be able to immediately try to get these query key and value vectors simply. Now, why did this completely blow up the entire field of AI? There are several reasons. Because first thing is the RNNs, whatever we had, it tries to remember stuff from the beginning to the end and stuff them into a singular vector. And now this might be very bad because it might just uh, forget about what the context means in the beginning, forget about the words which happen at the beginning. But in this case, with attention, that problem just disappears. When you have a sentence, let's say with even 100 words, the model can still play perfect. The model can still pay perfect attention to all the 100 words, and then can adjust its context in such a way that it might understand all the 100 words and be able to answer with any of them. So there is no information bottleneck, no compression, no forgetting, nothing. Every word will be equally accessible at each step. Now the second reason is the once this one is very big because RNNs had to process each of these words sequentially. So the had to be processed first, then cat has to be processed, then on has to be processed. After on itself, it was able to move to the next word. After cat itself, it was able to move to on. So it has to perform everything serially. But the attention mechanism, you can compute the attention for all the positions. You can compute the attention for the word the, you can compute the attention for the word cat, ran, away. All of them can be immediately performed by parallelly or simultaneously. So this made training to go from weeks or days, but to take even some few hours. So if you're training on millions of sentences, this speed up will absolutely change how much time you'll save. And then attention is not just for translation. You can use it for summaries also. So you can use it for summaries, you can use it for question answering, or you can use it for image captioning and so much more. So like it is a general purpose mechanism, and it will focus on what will actually matter. Now, where this attention mechanism really kicked in was in 2017. Some researchers in Google, they published a paper called "Attention is All You Need." Now they said, you know what? We'll throw away RNNs entirely. Okay, we'll build a model only using attention mechanisms. Now this model is, as a lot of you might have known, is called as a transformer. Okay, and that transformer architecture, it became the foundation for literally everything which you've seen till now in modern AI. You can start with BERT and you can go to ChatGPT 3, GPT-4, and then you can go for Google's Gemini. You can go for Claude's Anthropic, everything. So you can understand the weight of this attention mechanism's power. Now, whatever I've shown you till now, this is called as cross attention. Why is this called as cross attention? It is because you are attending from one sequence to another sequence. But there is something called as self attention. What is the self attention called? Now, this is what makes transformers so powerful. In self attention, a sentence, whatever you have, will pay attention to itself. Okay. So, let's say the animal didn't cross the street because it was too tired. Now, when the model is processing the word it, what will it try to do is it will use self attention and figure out what it here refers to. Now, what does it refer to? Will it be the animal or will it be the street it is referring to? It will try to figure it out. Here's how it works. So, if every word in here acts as a query, okay, so every word in here acts as a query and it also has a key and a value vector for each word. So now the query for the word key, the query value of the word it will try to go find the appropriate key value which has the most similarity. So it will search through every key value in the data, through animal's key value, didn't cross the street, everyone's key value. It will search its query vector against everyone's key value. And then it will understand that, hey, this it, whatever we are trying to tell, is referring to the animal rather than the street itself. And in transformers, this happens with multiple layers and multiple attention heads per layer. So each attention can focus on different aspects. So one might focus on, let's say, nearby words, or other might focus on verb and subject relationships, other might focus on long range dependencies, etc. So they'll all work together like this, and it will build like an extremely rich representation. Now that is how the language models usually understand this context so well. They're not just seeing words in isolation, they use every word's representation. Every word's representation is being built by paying attention to all the surrounding words. So basically, attention mechanisms will let the model dynamically focus on the different parts of the input instead of trying to cram everything into this fixed size representation like this in whatever we've seen in RNN. Now, the query key value mechanisms will give us a learnable way to try and compute of how much attention we need to pay to each part of the input. Before attentions, we had models which struggled with long sequences, but after attention, we got a lot of other models which will basically define the generative modern AI revolution you're seeing today. So we went from models which could barely translate sentences to models that can write essay, codes, have conversations, and understand nuance. So pretty wild that such a intuitive idea, just letting the model look at what it needs, ended up being so powerful, right? Now that is attention mechanisms. So if this helped you understand attention, make sure you go smash that like button and definitely subscribe if you haven't already, because we're just getting started with this AI interview questions kind of series. And if you have any questions, throw them in the comments and I'll try to answer them. And I'll see you all in the next one.